Welcome back. Today I want to talk about binary choice models. In binary choice models, the dependent variable is, well, a binary choice. So it's either yes or no. In terms of labeling, it could be labeled as a 0 and 1 or any other label. So when we think about our regression analysis, we had a dependent variable that could take any value. And we make our model predictions. They could go, in theory, from minus infinity to plus infinity. But now our outcomes are limited, they are discrete. So how do we model, in this case, such discrete outcomes? So put differently, if I want to make a prediction, I can't predict a 0.7. It's meaningless because either the event occurs or it doesn't. So in terms of predictions, we focus on probabilities. But as you will know, a probability is not plus infinity or minus infinity. A probability occurs in the range from 0 to 1. So somehow we have to map our standard linear model to an interval from 0 to 1. So this is what I will discuss in this video. I will talk about how we do the modeling. We talk about logistic and probit models, and we see an implementation in Stata. Now let's get into it. Again, whenever I'm a little bit, confused, which happens most of the time, I start drawing a few pictures and just, think about this a bit more carefully. So if we go back to our standard regression problem, we have here a dependent variable and we have here an independent variable. And after doing some fitting, we would get a straight line, so say this line here. And of course, being a straight line, you can extend it up to minus infinity and you can go up to plus infinity. You don't have any constraint whatsoever. So if we want to model a probability, on the other hand, we have to impose some boundaries. We can't go on to plus minus infinity. So basically the problem is moving from something which is not restricted by any means to an interval from 0 to 1. This is in fact our problem. So how can we do a model where we move from this to that? Now, in terms of notation, we just denote our linear model as Z, and you can imagine Z being something like a constant term, and then you might have several independent variables, another beta 2, x2, and so on. Yes, this is our standard linear model. So how can we move from this model to a constrained interval? Now, there are different ways of approaching this. One way is to use a logistic regression. So in a logistic regression, we transform our model as follows. We take the e function to the power of z, 1 plus the e function to the power of z. Now, what does that actually do? Now, this transformation will change our outcome accordingly. Yeah? So if we look here at this problem for different values of z, we can plot now a different relationship. Yeah, so in this case, if z is equal to 0, of course e to the power of 0 is 1, so you would get here 1/2, yeah, which is maybe somewhere here. If I take very large values of z, I could explore the limit of it. Yeah, so if I take the limit of z going to plus infinity, I can just divide by e to the power of z, and I basically obtain that. This term here will go to 0 plus, so this will go to 1 minus, so you approach 1 from below. So we are somewhere here, so that's our level 1. and you won't quite reach it. So it's a bit like you move up like this and you slowly but never quite reaching converge to 1. If you take sets to minus infinity, this will approach 0 plus, so it converges down there to 0. So now we in fact manage what we wanted to do. We do transform our linear model so that our outcome has to be in the range 0 to 1, and this we view as a probability. Now, it very much depends what the actual problem is and also what type of data you have. There are further complexities which we can explore in other videos when you have very unlikely outcomes. So if you are in a so-called rare event problem, where the positive or the negative outcome is very unlikely, so less than 5%, you have to be more careful about modeling, because very often these models might understate rare events. But in a general setting, most of these problems referred to an outcome which you can observe, but an underlying decision problem which you cannot observe. So it's what you call a latent variable problem. So that's a very common approach, in particular in management, finance, and economics, but also in many other settings, where we assume that we don't know exactly what's going on inside this black box of decision making. We only observe the outcome. So whether someone is doing something or not, whether a company is going under or not, but we don't know exactly how close the decision was. Yeah, so that is our perspective on these binary choice models. If you want to explore this further, I recommend the book by Hayashi on econometric theory, chapter 7, where this is explored in the context of the profit model. Now, we already covered the idea, and that's actually enough for us at this point, and this is the outcome when we look at the logistic distribution, so that we can squeeze it into the interval from 0 to 1, which we then might interpret as a probability. Now, in terms of the modeling choices you have, there are two main models used in binary choice modeling, the logistic model and the probit model. There are differences between these two models, which I might cover in a separate video. Just leave a comment down below if you want me to explore this further. So in the end, when you run these models, you have to be aware what you do is a numeric approach. Yeah? So you conduct a so-called maximum likelihood estimation. Again, I won't talk about the theory in this video, but just to mention this, and this means that it's not always guaranteed that your numeric method converges. So you might have non-convergence. And sometimes the approach to deal with it is to change between a probit and a logistic model. That can sometimes help. Sometimes you have to change also your model specification. So basically adding, removing a variable. That might also help with conversion. So you have to explore the underlying problems in further detail. So what I want to do now is we will move now into Stata and again get our hands dirty and do a default prediction. So what we do is we look at a data set of company defaults, and then we use a standard classic model which is used to identify default risk, the so-called Altman z-scores. There's a lot to talk about the Altman z-scores, and again, if you need some more details, just leave a comment down below. We can always do another video to explore this further. But for our purpose, the Altman z-scores is just a bunch of independent variables which you see defined here that should predict the likelihood of firm default. And I already started doing some work because it will take us otherwise too much time to type this all up. Of course, you find all the code in the GitHub repository. So the first things here are just literally defining variables, introducing labels. So there's nothing really massively exciting going on. Yeah, so here it all runs through, so that's fine. A quick describe, so it's quite a large data set of firm defaults, which now contains all the different factors you need. So this is F1 to F5, so these are the Altman set scores. Good. Now let me just start the model. We now first do a standard, box standard logistic model. So let me just type this, so normal logit model. Just make a bit of space so it's easier to see that. So I just do logit. Our dependent variable is called default. So this is the default risk. Actually, this is the default. That's the default outcome. F1, F2, F3, F4, F5. Or we can just do F asterisk, that would also do. And I'm just running now this logistic model, and we have a quick look. Okay. Now first you notice here you have iterations. So this is what I mentioned before. This is the numeric method, just running through this. And we need only 6 here, and it converges. So that's quite promising. If it continues for too long, I would be a little bit suspicious. Now we see here observations in total 42,000 and a few more, so that's quite useful. We have here a likelihood ratio test applied, which would suggest, looking at the p-value, that the model as a whole doesn't have an amazing level of predictive power. Yeah, so here the p-value is clearly above 0.05, which is not a good sign in terms of, predictive power of your model. Now you note that in the case of logistic models and also probability models, you don't really have an R-squared. So not like in OLS regression. However, many people report a so-called pseudo R-squared, which is not quite the same. It's a different definition. This is based on comparing likelihoods. It's a different definition. It's the so-called McFadden R-squared. And again, if you want some further details, just leave a comment below. We usually don't focus much on it. So in terms of what I would report here the quality of a model using the p-value, which isn't very impressive, of the likelihood ratio test. Now, in terms of the individual explanatory variables, so none of these Altman set score factors seem to have any predictive power. But again, in this kind of analysis, the focus is not too much on these individual factors. The main focus would be as a whole, can I predict something? So that's the main focus in our setting. Now, what I add to this model next is I will add firm size, because firm size tends to be quite a good predictor of default. And we define firm size above as the ln of total assets. We have done this before. So let me just run this model. And you see now that the game has changed quite a bit. Again, it converges very quickly after only 8 iterations. You see very clearly that the model now as a whole has some predictive power. So you can clearly reject the null that none of these variables has predictive power with a high degree of certainty. So the p-value is clearly below 0.05. Now looking at the individual independent variables, clearly firm size jumps out as being highly significant. Yeah, so there is no doubt about this. And as you would expect, smaller companies with negative coefficient have a higher risk of default. Yeah, so this is an interesting outcome and certainly something to explore further. Now, very often when I do these models, I like to visualize it. So a nice way to do this is to predict the probability of default of a probability of any positive outcome. And I can do this after the logistic model using predict. I call this prop for probability and use the option PR for probability. So I'm just now running this line here, and that predicts my probability. So that is a nice visualization of this relationship. And now it might be useful to have a little scatter plot and simply compare the prediction with firm size and see this relationship in this particular case. I'm just plotting this, and now you see this emerging. And definitely it's quite interesting that for smaller companies as a tendency, first of all, what you see, you get more variability for sure, but also you see that there is a tendency for a higher default risk. So that's useful to know. Now, in the end, how can we assess the quality of this model? Now, for that, it would be useful to see actually how many defaults do I have in total. Yeah. So if I simply do a summarize command and just have a little look about the general probability of default. So what you notice is that it's not very likely in this sample to see defaults. Yeah. So probability of default is somewhere around 1%. So it goes back to issues which you get in rare events. Yeah? So here we are at quite low levels of probability. Now the trouble is when we look at our model predictions, which might be also maybe useful to put in the same, we then have to think what's a good cutoff point, at which point I would argue that a default is more likely. Yeah, so of course here, this is now a restricted sample. Again, the probability which I predict is quite low, as you would expect. So the thing to now discuss is what's a high enough probability to trigger the label default. So, and this is something you really have to try to figure out. So what I tend to do is, so after simply checking now the total number of cases, and now we know there are very few cases, it might be useful to do a post-estimation analysis. And here I use the stat method and class for classification, and I specify no different cutoff points. These are the cutoff points based on your predicted probability. You have to play around a bit, so I now put in 0.025. So this you have to check. Again, it might be maybe useful to do a summarize command with detail, so to see really the upper and lower bounds of it. That might give you a few hints what might be a reasonable level. So when we go up here to the top end of it, yeah, so maybe, I think maybe this is a little bit high what I select, so we can maybe play around and later reduce maybe to 0.08. But the issue is, of course, and you will see this in a minute, you can make mistakes both ways. So let me just run now this classification. And here you see a full picture of what the model can and cannot do. It's not looking impressive to be expected. It's a difficult problem. Default predictions in companies is a difficult problem, and it's well known to be difficult. So here you see the classification. Plus would be a default prediction, minus would be there's no default, and this is the true state. So what you can notice here is I get default predictions in total 115. So 115 times I say there is a default, but only in 2 cases I'm actually right. Now this is not fantastic, yeah, and you see sensitivity is very low, yeah. So basically this gives me the probability of me classifying correctly if the actual case is a default. So that's not amazing, that is quite low. Yeah, so this is certainly an issue. And the other problem, of course, is I make lots and lots of mistakes, because there are many cases where I would indicate a default, but actually there isn't one. So that's the other problem. So and this depends, of course, on our cutoff points. If we modify the cutoff point, we of course might gain something in one dimension, but not in the other. Yeah, so that's the other problems. If I reduce this a little bit, make it more sensitive, you might, and you see that here, get more cases right. Yeah, but of course you get an awful lot of false positives in this case. Yeah, so here we would say that all these companies are at default risk, but actually they don't default. So it's not amazing. So at the moment, I think this model wouldn't be good enough for commercial use. There's one more thing which you can try, is you can visualize it using L-Sense. So it's just a visualization of what we just saw in the table, which shows here again your for this particular problem, your sensitivity, which isn't amazing, and very clearly that tells you already what you know, that this model should not be rolled out in decision making at this point. Good, so that's all I wanted to cover regarding the binary choice models. I see you in the next one.